Okay, so it turns out I forgot to turn on the mic in the previous lecture, so we have to start from the top. Let's start from the top. So we talked about the black hole string correspondence as being an overarching framework for matching properties of black holes and strings at one value of the coupling, where G square is 1 over the entropy. We take G small and the entropy large. And we are supposed to be interpolating almost adiabatically between those two regimes, and we're going to talk about what that precisely means. And what we're going to imagine is we're going to hold the entropy fixed, and once we add angular momentum, we will also keep that fixed. So those two will be our adiabatic invariants, approximate adiabatic invariants. And we're going to discuss this. We're going to write down diagrams where we have this adiabatic invariance, where we look at how other properties change as we change the coupling, G squared. And we said that because the entropy, the mass, and the coupling, there's a formula for that that relates those three. If we keep the entropy fixed, but change the coupling, then the mass is going to change. And so while we have a black hole with some mass on one side, a black hole with some mass, a string with some mass on the other side, they do have different masses. The entropies are the same. It means that the masses have to agree at least at this one point, the correspondence point, where we're supposed to equate those two objects, but not in principle anywhere else. And so what we're going to talk about next is the matching of these other properties at the correspondence point. So if we find that as we hold the entropy fixed and change the coupling, that black holes and strings have properties that as we go to the correspondence point don't agree, then we're doomed. Okay? So all properties of these objects have to agree at the correspondence point. And so now we're gonna look into whether that happens in order to give more evidence or test this proposal of black holes being equated with strings. So there's some now details of the matching. And what we're going to look at is how the mass behaves. We're going to look at the size of strings and black holes. We said that when you have a coupling that's neither 0 nor infinity, then things evolve. So we're going to look at decay rates. And then there's a list of things that you could imagine comparing. And the important point is that there's a correspondence only if there's an approximate notion of adiabaticity. Okay? And in order to realize this correspondence, I mentioned already two things that we can imagine doing, so physical realization. The one was we are working in our dilaton lab where we can send a dilaton wave and we can dial the strength of that dilaton wave. And the other thing that I mentioned was slightly different sort of story there. Is when the black hole evaporates. We imagine there to be a string description once the black hole becomes small enough. Okay? So we're still going to work with the static black hole and static string. And once we've discussed some of these details and the adiabaticity condition, we're going to move on to rotation. So the first item is, let's look at the mass. So again, we fix S and we vary G. And so that means that the mass gets renormalized. Now I'm going to switch I'm going to mirror this. So my string will be on the left and my black hole will be on the right. Because I'm going to draw the following diagram. I'm going to do this. I'm going to write the mass in string units as a function of the coupling. So for a string, We saw before how entropy and mass are related. So the entropy is given by the mass in string length, or if I write it, if I put the string units on the other side, then we have a formula for the mass. And then there is subleading corrections. And these corrections come from strings evolving, strings interacting, and this is of order g squared. So if I start at some value of s here, that's the entropy, you can see that the mass for the string is roughly constant. And then it has like order g squared correction, which makes this tilt down a little. I'm gonna draw here the special value of the coupling where g squared is 1 over s, so that's the correspondence point, where my string description should go over into a black hole description. Now how does the mass of the black hole go? Well, again, I invert the formula for the entropy that I had, and I write this in the same units. So ms over g square s, and then in d dimensions I have to sprinkle these factors of d minus 3, d minus 2. So that's the black hole. So I can see how that goes. So if I divide by ms, then I have a 1 over g squared. So this line is g squared, so it's the inverse. So this does something like that. And you can check that when g squared is 1 over s, that these things match. So this is at g squared 1 over s, and the two masses match. Okay, so that's the first thing. We have checked that while we keep the entropy fixed and change the coupling, the masses of the string and the black hole smoothly agree at the correspondence point. Okay? Next thing, size. So we said that we start out with our big fat black hole, we decrease the coupling, the black hole becomes smaller, the curvature becomes larger. At some point, we reach the correspondence point, where we saw that the black hole at the correspondence point, so at g squares of order 1 over s, the correspondence point, the black hole will have a size of the order the string scale, string length. But what about the string size? So we start out with a free string, then we turn on the coupling. What can a free string do? It has oscillators. These oscillators can do some jiggly motion. So they do some kind of random walk type motion. So this is how I can model a string, the oscillators of a string. And as you might know from your undergraduate physics course, so there's a random walk length, and the size of the system is given by the square root of that length in string lengths. And that is given by the square root of the entropy. And the square root of the entropy, so S is a large number for us, which we keep fixed. So this is much larger than the string length. So if my string does a random walk, its size is square root S times LS, which is much bigger than LS. So it looks like we have a problem, because the string is very floppy. We have a free string, it's very floppy, we increase the coupling. The string is still very floppy at the point where it should match onto the black hole. But the black hole is of string scale size. So are we doomed? Can we go home now? Or is there something that we forgot? What? I didn't hear. Somebody just said that we forgot something, or? Okay, good. Okay, that's the right answer, if that was the question. But the question would be, what did we forget? Well, let's see, we take the string and we talk about the duplicity in a moment, and I will show you how, in what sense we can have them go into each other adiabatically. But there's something that we forgot. So the first paper of Horowitz and Polchinski had like sort of these kind of ideas, and there was, so these kind of ideas in them. And then they wrote a second paper because of this issue. And the second paper was about how to make the string of string size, string scale size, string length size. How to make the string smaller so that it matches onto the black hole. So the key word here is that we neglected the effect of self-gravity. When you include that effect, the string will become more compact. So that will shrink the string to LS, such that it can match with the size of the black hole. So this is in the second Horowitz-Polchinski paper that I listed in the beginning. We will not talk about that. We will not talk about a self-gravity in this lecture. They have come up with some model, which goes under the name of thermal scalar. And it would take too much time to discuss that. And we will also not actually include self-gravity when we go to rotating strings. So that's why I cut that out. But you can go to the paper and read it up. And the more recent paper by Chen, Maldacena, and Witten that I listed in the beginning from a few years ago makes this whole picture, including self-gravity and this model that makes the black hole, that makes the string shrink, more precise. So you can also go there for more recent work in that direction. Okay, so once you do that, we can also make a smiley face here, because the two agree. Okay, so now the next thing that I have to do is I have to talk about dynamics so that I can talk about decay rates. So when the coupling is neither zero nor infinity, then black holes and strings evolve. And the question is, what can they do? So what about strings? What can strings do? Take a massive string, let itself interact. What can it do? Yeah, it can split, so there's fragmentation. And it could emit radiation. It could emit some light strings. Emission of light strings. What can a black hole do? Yeah. So quantum effects. Via emission of Hawking radiation. Okay, so for example, we would like the black hole go over into a string before it has evaporated, because if we wait too long, then there's no black hole anymore. So our adiabaticity window should fall within the lifetime of a black hole. What do I want? Yeah, let's do this. So one of these other papers that I listed in the beginning by Damour and Veneziano, they looked at decay rates. So that's something else that we should match. So we're going to draw the decay rate gamma as a function of G string. And again, this blue line here will denote the correspondence point. So let me write here 1 over L string. Then down here, well, I have g square. Yeah, let me write this. G square is 0. And then somewhere over there, we'll have g square is infinity. Those would be the stationary points. So my decay rates will go either here or here on the string and on the black hole side. So for strings, the decay rate goes with the square and the coupling and the mass, and expressed in terms of the string length and so M is not an adiabatic invariant. I also always want to express things in terms of adiabatic invariant. So the thing I have to replace it by is the entropy. So that's G square S and then LS minus 1. That's the decay rate of a string. And this goes something like this, roughly speaking. Okay? And it reaches 1 over LS when G square is 1 over S, the correspondence value. And then for the black hole, the decay rate, well, we just said how it decays. Limits Hawking radiation. So this is proportional to the temperature of the black hole. The temperature is inversely proportional to the horizon size. And that we already computed. That's G square S to the power 1 over minus d minus 2 and LS to the minus 1. Okay? And so that looks something like this, roughly speaking. And when G square is 1 over S, this becomes 1, so this also reaches the same value, 1 over LS. Okay, so this also checks out. Okay, so now what about this adiabaticity notion? And by the way, you could go on and find out the properties and try to match them. There is projects for you. So we have to, when we say we match black holes and strings, this has to happen in an adiabatic or almost adiabatic way. So the way we change the coupling should not be non-adiabatic. Now, since things evolve, there cannot never be exact adiabaticity. So we will have to come up with some approximate notion. So here's the approximate notion. So we want that the rate of change, let me call it delta T inverse G for the coupling. The rate of change is G dot over G. And if you remember, G was e to the phi, the dilaton. This is the change of the dilaton. So what do we want? Well, on the one hand, we want this change to be slow enough so that we don't excite the system. If we kick it too fast, it gets excited, and then we're not talking about the same system anymore. Slow enough to not excite. How can we do this? So we said we're going to change the coupling, and we were working on our dilaton lab. We have this wave that we are sending, and then it changes coupling in different space-time regions, and we can turn black holes into strings by doing that. But how do we set this up so that we don't excite the system too much? So we have this dilaton wave. You send a wave through something. Think of our gravitational waves that went through the detectors. What do they do? They jiggle stuff. Here we want the system not to get excited. So what does the wave have to have such that the system doesn't get too much excited? A wave has energy. Yeah, what does it mean in terms of wavelength? Yeah, so if you choose the wavelength to be long enough, the system, then we can set it up in such a way that it's quote unquote slow enough. I haven't told you precisely what we mean by this, but roughly speaking. So it has to be slow enough so that the things get not excited, but if we wait too long, if we make the wavelength super long, and we wait too long, then the black hole is gone. Okay, so it also has to be fast enough. So what happens when the black hole evaporates? What happens to the entropy? What happens to the entropy of a black hole when it evaporates? It decreases. But what did we say we want to keep fixed when we compare black holes and strings? The entropy. So we don't want the entropy to change too much. So this transition has to be fast enough to stay at roughly constant entropy. And the thing to keep in mind here is that at any finite g, we have radiation. And so we have to determine what fast enough means in terms of how much radiation do we have from the system. And we don't want it to radiate too much. So given these two conditions, I can come up with a range of rate of change such that I can call, when something happens within that time scale, I can call it almost adiabatic. So we will refer to this as Goldilocks adiabaticity. You know the story about Goldilocks and the three bears? Okay, if you don't know, go look it up. Homework. Okay, so Goldilocks adiabaticity for the change of the coupling, G, not too slow and not too fast. So we look at both how the systems radiate, on what time scale, and we impose that the entropy change while it's doing that is small. On the other hand, we impose that the wavelength of this dilaton is long enough. So that one's easy because the size of the system at the correspondence point is the string size. So that bound here will have to do with the string length. And on the other hand, this bound is about not changing the entropy too much. So this bound on the other side has to do with the combination of the entropy and the string length. So this is the bound. The rate of change has to lie within this window. And these two bounds come from these two considerations. Now, can this be satisfied in many situations? Well, S we took to be a large number. We're looking at the macroscopic black holes to start with. So this is large. And because this is large, you see that there's ample room to be within this window, depending on how large S is. So because S is large, there is ample room to satisfy this Goldilocks adiabaticity condition. When would this be an exact adiabaticity condition? So when the entropy is infinite, then we could talk about adiabatic notion. But we're working with sort of real systems where the entropy is not infinite, it's large. And we will never have an exactly adiabatic notion, okay? So it's about time scales, and this is the time scale so this is the window within which we will try to turn strings into black holes and vice versa. And now we have to compare this window with whatever crazy stuff black holes and strings can do when their couplings are changed. Okay? Good. So we have now been setting up the black hole string correspondence for static black holes. We said we fixed the entropy, we changed the coupling, and that means that other quantities get renormalized. And we have checked that various important quantities, such as mass, size, decay rates, they're different away from the correspondence point, but where they're supposed to match, they do. Okay, so what we have done so far is for generic black holes in arbitrary space-time dimensions, but restricting to the case of static objects. Okay, so far, static correspondence. And we have seen that we can match various quantities, and we can say that the entropy of a black hole can be understood at the correspondence point by this transition into strings, and we understand what the microstates, what the degenerative states of a string are. Okay? In what I have said, there are some limitations. And the limitation is, of course, that we don't know what the entropy is at all values of the coupling. I mean, what we would ultimately like to do, we would like to understand quantum gravity well enough so that we know what the microstates of a black hole are at the same value of the coupling where the black hole exists. But we don't. Okay, so that's one of the big open questions. The black holes of general relativity describe extremely well many things regarding quantum aspects of black holes. Even effective field theories even seems to be a good description when talking about evaporation of black holes. So it seems to be extremely good, but we don't know what the microstates of these objects are at the value where the coupling is the same as well the black hole exists. So what we're doing, we're changing the coupling, and we're seeing if we have a correspondence with other objects as we do that. That's the tool that we have available. If we were powerful enough, we could do the other thing, but at least at this point, we don't seem to be powerful enough. So it is about a parametric matching. So the entropy stays fixed everywhere, but it is a parametric matching of all the other quantities. There is no exact equal sign. We have dropped order 1 numbers. So that's why it's a parametric matching. And only at g square is of the order 1 over s. And this is one value. Okay? So that's one limitation. Another limitation is, well, that comes with the territory. The adiabaticity is only approximate. But it exists within this Goldilocks regime. So the nice thing about supersymmetric black holes is that we can do an exact matching at some correspondence value, and we can we have an adiabatic notion. And then the other thing is, so we saw that to match sizes, we had to include the effect of self-gravity. So it's not good enough to just study weakly coupled strings and black holes in GR. We do have to include the effect of self-gravity. But I also said that we are not going to talk too much about that from now on, because what we're going to do is we're going to try to give a broad brush picture of how things work, and then you can try to fill in and do better. Okay, so that was for the static case. And now the point is that once you spin the black holes and the strings up, new features will arise. And there will be these puzzles that we discussed in the first lecture. And if you want to make the black hole string correspondence work, it needs to work not only for static black holes, but also for rotating ones. And so we have to resolve these puzzles. Otherwise, it doesn't work. Okay, so now let's talk about the black hole zoo. well, actually black hole strings too. So it turns out that as we increase the number of space-time dimensions, there are more types of objects that arise. And particularly on the black hole side, there are distinct objects from the spherical symmetric black hole, which we also have to keep in mind. And because there are so many different types of objects, we would like to put some order in this black hole zoo. And we can do that by introducing some characteristic length scales to distinguish between these objects. So I will introduce two characteristic length scales. One I will refer to as the mass length, and the other one as the spin length. So what's the mass length? So the mass length is given essentially in terms of the scale of the black hole, so the horizon. So there will be some factor of gm, and then in d dimensions, sprinkle these factors of d. So it depends on the mass. And then there's the spin length, which, well, it involves the spin. Okay? And now I can look at two different regimes. One is where the mass length dominates, so it's bigger than the spin length. And then one where the spin length dominates. So what happens when the spin length is smaller than the mass length when I'm thinking about black holes? What kind of black holes can I have? Well, the black hole is dominantly described by mass. The spin is not, not very large. So what I have is like roundish black holes, which are unique, roundish, and dynamically stable. And similarly, I have roundish strings that are dynamically stable. So I will refer to this regime as the Kerr regime. Okay? Now I spin up the system, and I go to what I'll refer to as the ultra spinning regime. That is when the spin length is bigger than the mass length. So what happens when you spin up a black hole? You have this nice roundish black hole. Now let's say we spin it up with rotation plane orthogonal to the z direction. What happens to this roundish black hole? It squeezes, good. So if I spin it up a lot, it kind of pancakes. At large enough spin in dimensions 5 and higher, I can have different objects, with different topologies. So I can have a black ring, for example. I can also have objects that are called black bars, which emit a lot of radiation. And then, since 2023, new objects have been found that contain both black hole and string components. So these are sort of hybrid objects. So there's a roundish black hole, and then there is a string sticking out of that black hole that carries a large amount of rotation. And I can have similarly pancaked strings on the string side, and well, this guy is a hybrid. So this actually was very fortunate that this paper came out a few months before ours, because it turns out that these objects actually play a role in the black hole string correspondence with rotation. So these roundish black holes are called Myers-Perry black holes. Then black rings and stuff have been discussed by Emperor and Rial. And then these hybrid objects were discussed by Deng, Grudzinov, Levin, and Vilenkin last year. And what is special about this object is, well, okay, we have kind of different shapes and topologies. And they're dynamically unstable. Okay, so if we are in dimension 5 and higher, so in 4 dimensions we can have 1 rotation plane. In 5 dimensions we can have 2 rotation planes. As we go up in dimensions we can have more rotation planes. And things will become quite complicated. If we want to distill the main feature that arises due to rotation, it turns out it's best to just have a single rotation plane. Because then in all the other planes, there's no rotation. It's like the static case. And we're going to see most dominantly what the effect of rotation does to the system. If you give it rotation in all rotation planes, then you kind of average out the angular momentum. And it becomes, again, more like the static case. But if you want to see like the effect of spin, and we take spin very large, then we just pick one plane and crank up the spin. So we're going to focus on a single rotation plane. And we're going to, again, express all our results in terms of this adiabatic invariance, entropy, and angular momentum. Okay? So let's talk about d equals 4. So we had this black hole, which obeyed the Kerr bound. And we had the string, which obeyed the Reggie bound. And then we said that those two are not the same. And in fact, we found that actually the Kerr bound is much smaller than the Reggie bound. So if you go back to the formulas that we wrote down before, on this side we have the mass squared in string units. On this side we have the mass squared in string unit times the coupling squared. The coupling is smaller than 1, much smaller than 1. So the Kerr bound is much smaller than the Reggie bound. So if I then draw black holes on the upper side, strings on the lower side of this line, and the line is cranking up angular momentum from 0 to, well, in principle, infinity. I put the Kerr bound here, put the Reggie bound there, and, well, I know I can have black holes here. I also can have strings here, all of them roundish. As I crank up the spin, there will be random walkers that I have to use in order to crank up the spin. So there will be fewer random walkers. And then there will be some components of the string sticking out to give it rotation. But I have no black hole solution there. So that was the first question that we posed in the beginning. There seem to be highly spinning strings, which in 4 dimensions do not seem to have a counterpart on the black hole side. So that's puzzle number 1. What was puzzle number 2? So puzzle number 2 in 5 dimensions and higher. Again, I'm going to draw J here. Black holes, black objects upstairs, strings downstairs. I will still refer to this as the Kerr bound, even though it's not about, there's no Kerr in high dimensions. So those are other black holes. Okay, Reggie bound. In higher dimensions, again, we said there can be black holes. So there's still some sort of roundish black holes, some roundish strings. Then as we crank up the rotation, okay, we have strings that flatten out. We again have strings that are highly elongated as we approach the Reggie bound. We have black holes in all values of J, because there is ultra spinning black holes that exist with arbitrary J. So we have these pancake black holes, we have black rings, and we have these bars, and then we have these hybrids. But we have nothing here for the string because there's no spinning string beyond the Reggie bound. And if you, okay, maybe I should have drawn these objects more to the right. But if you compare the strings in this regime, so I should have drawn everything a bit more to the right, just to be clear. Because if you are near the Reggie bound, they're still sort of roundish black holes. They're a little bit pancaked, but they look very different from these rods, from these rotating rods. And we said in the beginning that these two puzzles can be resolved if we correctly take into account dynamics. So let's look at what can happen so that we can make sense of this. So we talked before about what can happen to strings, like they can fragment, they can emit light strings. Let's talk about black hole instabilities. So let me draw again this line here with J Kerr. And all that is until the Kerr bound is my Kerr regime. This is when the mass length is bigger than the spin length. And then everything to the right of here is the outer spinning regime, where the spin length is bigger than the mass length. So here we have these roundish black holes. Well, these roundish black holes, they're classically stable. So that's all that I have to say about them. Then in the ultra spinning regime, we have these pancake black holes. And we have rings. And they're unstable. So black holes in the bigger or equal than 6 dimensions are unstable, and black rings in the bigger or equal than 5 are unstable. And now the question is, what can they decay to? Let me write this over here. So what do you think are the instabilities that a black hole can have? How can a black hole decay? Okay, this is when we go near extremality. Disclaimer, we're not talking about the black hole string correspondence near extremality. This is actually a range of black hole parameters where we don't have a good handle on the black hole string correspondence. Thanks for asking. So I told you that there are these objects that look like bars, and these bars spin very rapidly. Now, and what's a bar that spins very rapidly? It's like an antenna. And what does an antenna do? It radiates like crazy. So it wants to shed off its angular momentum by radiating stuff. So you can call this death by radiation. Okay? So these objects are unstable. You know, they can exist here, but they will emit their angular momentum by radiating. Now what about black rings? So let me zoom in on the ring. Let me draw a very thin ring. What happens if you poke the ring? So if you poke the ring and you put some perturbation on top of the ring, what happens if the ring is thin? It can pinch off, no? So this is called the Gregory-Laflamme instability. Ever heard of it? Okay. So this instability allows the black ring to pinch off and fragment. Let's say you pinch off here, and then you get something like this, no? So this is death by fragmentation. Then we can also have these hybrid objects, and I think I mentioned this before. So there is like a black hole-ish object in the center, and then a string sticking out that carries the angular momentum. And it will shed angular momentum, and then the string will shrink, 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 and then it will become more and more a roundish black hole that is rotating. Okay, so I have introduced all the details that we need in order to now draw diagrams and see how the correspondence principle should work for rotating objects. So I'm going to draw the correspondence diagram. It has g squared on this axis and angular momentum on that axis. We have the correspondence point, 1 over s, or, oh, sorry, I'm drawing it upside down. So actually, this blue one is now the stability bound, the Kerr or stability bound. So before here, I've been, well, somewhere before, I've been drawing it the other way around. So this is the Kerr stability bound. And the correspondence point is on this side, is when g squared is 1 over s. So this will be the correspondence point. This shock is really terrible. Okay? So strings will be on the lower side and black objects will be on the upper side. And then we're distinguishing between the Kerr regime and the ultra spinning regime. Okay, so maybe let me say this here. Kerr regime and ultra spinning. Okay, let's first start with strings to black holes. So strings we can have in any dimensions, and we didn't distinguish between 4 dimensions, 5, higher, whatever, unlike for black holes. So let's start with a roundish string. What happens to a roundish string? A roundish string is mostly stable, so that falls within my Goldilocks adiabaticity regime, right? What happens to a roundish string as I crank up the coupling? I want to turn it into a black hole. So what black hole does it turn into if I crank up the coupling? A roundish black hole, yeah, obviously. So there's nothing big happening here. This is, since we are in this Kerr regime, this is like the static case that we had before. These are almost roundish, they are sort of stable, so that's like in a static case. Now in the spinning regime, we can have these random walkers in the center and then a string carrying some oscillators carrying the angular momentum. What does that turn into? And so this is for any dimension now. So we have already discussed the kinds of objects that exist on the black hole side. What could it become? We're in the regime below the Reggie bound, but highly spinning. Any ideas? Yeah, say it again. There was the bars look like that. So yeah, so there's bars. Or we could also have the random walkers in the center of the string become a black hole first and have this string component still sticking out. So those are these hybrid objects. And then these hybrid objects, they radiate away the angular momentum and become more roundish black holes. Okay? And so now this resolves the first puzzle, because we said that there was nothing here in 4 dimensions that we could match onto. But as we follow a spinning string, so long as we're within the adiabaticity range, we can transition that into a black object, and then the black object does what it does. Okay? So we resolve puzzle 1. Highly rotating strings do have black hole counterparts, but they're in the form of non-stationary configurations. Okay? So now let's do it from the other way. And so there was nothing special about what dimensions we're in. Well, for the black hole, it's a bit different. So let's now do the black hole. Black hole to string. We're in 4 dimensions, so the only black holes that we may be interested are these roundish black holes, and what happens to them? If I transition them into a string, what does it become? A stable rounded string, yeah, the same that we had before. And then we may not talk about these other things because there are no stationary solutions, so we may not even think that we should transition them. Next up, black holes can, decay, and there's lots of interesting objects when we are in 6 dimensions and higher. So we have these roundish black holes, which again go to roundish strings. And then we have these more pancake black holes, and we have black rings. And now what happens to them? So these are in the ultra-spinning regime where there were no strings. So if I were to tell you that they transition into some string object, you will tell me that string doesn't exist. We want to match stuff with the same J, right? But there is no thing, there's no string with that J. These are ultra-spinning. So what can be the way out? Okay, so if we just said they were unstable and there's no adiabaticity, then we wouldn't be able to say anything here. But let's think a little bit harder about how they are unstable. So what did I just tell you about instability? Exactly. Or they fragment. So these objects can either turn into, like there are these bars that then rapidly, they lose radiation. They can turn into, well, these hybrid objects, or they can fragment into components. So let's say a single ring becomes a bunch of black holes. So this would be a multi-black hole object. And once I have this decay product, so this decay happens faster than my adiabaticity window allows. So this decay happens first. And now I have to look at the decay products. And if those decay products, if I can change the coupling to smaller values and are m within the adiabaticity window, then I can transition them into strings. So there's a new feature here, which is that these hybrids show up. But also I have these multi-black hole components, and these multi-black hole components will not become a single string, but a multi-string component. Okay? And this resolves the second puzzle. Which was that there are these ultra-spinning objects with arbitrary spin, but there's no string counterpart. Well, you have to first look at what these highly spinning objects do. They decay fast compared to the transition time scale. Then you look at their decay products, and what you see is that single string, considering stringless strings was not enough. There can be a fragmentation instability, and so you need multi-string states to fully describe this picture. Okay? Great. So this is the rough picture for correspondence with rotation. Here what I've been saying is that, so these objects, they will also spin down. So these components of the string will also spin down. And then they will transition into this multi-component string. It's hard to draw everything in a diagram. Okay, so now we have sort of laid out the broad brush picture for how the correspondence between black holes and string works with rotation. So before I said that the black hole string correspondence works for generic black holes in arbitrary dimensions, but in the first part of the lecture we just talked about static strings. Rotation adds a lot of rich features. So now we can say we have a correspondence picture for generic black holes including rotation. There is new elements that we had to consider compared to the static correspondence from the 90s. So first of all, we had to consider dynamics. We had to consider non-stationary phases. So that includes these black bars, black hole string hybrids, and multi-string states. And another thing that we're going to talk about in the moment is we have to look at the shape and size of black holes and strings with rotation. Okay? So in the static case, we said that black holes and strings, the sizes match, but they only do once you include self-gravity. Now, once you add rotation, you have, again, to compute from scratch what the sizes of the black holes and the rotating strings are, and you have to compare them. And so this is what I want to do in this last part of the lecture. But before moving on, are there any questions?
Why is self-gravity a problem?
It's not a problem, it's necessary so that you make the string compact enough so that at the correspondence point it has the size of LS, the string size. I mean the string length, the size of the string length. Because the black hole at the correspondence point, the horizon radius is of the order LS. Other questions? Was this all clear?
So does the inclusion of self-gravity changes the picture?
Yeah, so I have not talked about sizes of rotating objects yet. That's what we're going to do. We're actually not going to do self-gravity because remember, this was this thermal scalar model that Horowitz and Polchinski worked out in their second paper. And it turns out it's very hard to add rotation to this picture. It's a Euclidean picture. So once you add rotation, there will be eyes in some places, but you have to put them in the right places. And this hasn't been succeeded yet. I mentioned, I think I think I gave the organizers a list of references that may include recent attempts at that, but it's not satisfactory. We're not at a satisfactory point where we understand how this, what's called Horowitz-Polchinski ball, this region where black holes and strings near the correspondence point, we don't have a good picture yet with rotation. So what we're going to do is actually we're going to ignore self-gravity. We're going to compute sizes, and then we're going to try to compute, to extract from these sizes quantities that should be approximately adiabatic invariant. Because all sizes that we would compute, they change as you change the coupling. So they are not good measures that we want to compare. We want to need something that is an approximate adiabatic invariant in order to compare between black holes and strings. Okay, so let's look at that. So again, we said before, what happens when I spin up a black hole? It pancakes, right? Like it gets squeezed a little bit. And so the centrifugal effect here counteracts the gravitational attraction. A black hole with mass m so the mass of a black hole, you can view it as consisting of two components. On the one hand, there is heat, Ts, and on the other hand, there is mechanical energy. omega j, where omega is the angular velocity and j is the angular momentum. So if you increase the rotation, then that decreases the heat fraction for a total given energy. The geometrical counterpart of the entropy is the area, right? And so if you spin up the black hole, then that heat fraction gets smaller, the area gets smaller, so the black hole becomes smaller, okay? I can write down a formula that works for black holes that are slowly or moderately spinning, that relates the mass, now in Planck units, to the entropy and the angular momentum. So this is for absolute value j smaller or equal than s. And one thing that you can extract from this formula is that the effect of rotation comes in the form of the square of the angular momentum. And if you extract that out and make a number here, it is angular momentum squared over entropy squared. So this is something that we will keep in mind. So the effect, when we look at sizes of black holes, the effect of rotation should come in the form of j square over s square, okay? Now, a similar story can be said here for strings. So strings have oscillator excitations. And they come in two classes. We already talked about this before. What are those two classes? What can the oscillators do? Random walk and spin. So I can use the oscillators to do random walk, and that gives the black hole, that gives the string the degeneracy or the entropy. Or I can make them such that they coherently rotate. Okay? If I use more energy to make the string rotate, I have less available to make it random walk. So I can write down another formula here for strings that relates the square of the entropy to the mass in string units square minus 2j. And this is a formula that works for j of the order s squared. So from this we see that the entropy decreases if I spin up the string. Yes? So I give more energy to the random walk to the coherent rotators than to the random walkers. The entropy decreases. Now the thing is, the angular momentum naively appears here linearly. So the question is, when I compute now the sizes of black holes and strings, so for black holes I told you I should get something that is a function of j square over s square. It looks like for strings we may have linear angular momentum. And if the functional dependence in terms of j for the sizes of strings and black holes doesn't agree, then we don't have a correspondence. Or at least it would mean that we would have to add the effect of self-gravity, and hopefully that saves us. Okay? So from these two formulas, which relate the entropy, the mass, and the angular momentum for black holes and strings, it looks like the effect of rotation comes in as a square for the black hole, but linearly for the string. If I now compute the sizes of these two objects and I find that the functional dependence in terms of j is different between black holes and strings, then I don't have a correspondence. Or at the very least, it means that I have to include the effect of self-gravity, which is hard to do. What I'm going to show you in the following now is that things are actually much better. Okay? So we're going to compute now the sizes of strings and black holes, and we're going to compare them. And we find that the situation is actually much better than this naive picture would suggest. Okay. So let's start with what we expect. So we have the black hole. We're gonna compute two sizes. So we said we work in one rotation plane. So there's one plane of rotation, and there's two distinct sizes that we can compute. The size perpendicular to the rotation plane and in the rotation plane. And the same for the string. So if the objects rotate in this plane, which I will call the 1-2 plane, then I can compute this size and that size. This is really terrible chalk. And similarly here. So these are the two sizes that we're going to compute. I'm going to call them R perpendicular, R parallel. So the size perpendicular to the plane of rotation, which is this plane, and the size in the plane of rotation. And let's start with what we expect. So for small j, which means much smaller than the entropy, well, we had this formula over there. So what we might expect is that if we compute the ratio between the size in the perpendicular to the rotation plane and in the rotation plane, and let me subtract 1 from it, that would be the static case, then we expect this to go like j squared over s squared, actually with a minus sign. So this is what we would expect for black holes. For large spin, which means much, much smaller than the entropy, the black hole will pancake a lot. So there will be a pancake effect. Okay. What about strings? Well, for strings, I will argue that this is also what we should expect for strings, for small and moderate values of the spin. At large values of the spin, there's also a pancaking effect. But we already know that at large values of the spin, when we're in this ultra spinning regime, that there's all these dynamics going on. And so we actually are not required to find that the sizes agree in any way, because black holes will first undergo some decay. And so we do not expect that the sizes at ultra spin match between black hole and string. What we do expect is that in some regime where j is much smaller than s, but also of the order s, that we get some relation between black holes and strings, such that we have a correspondence. And you may now wonder, why am I not comparing our perp and our parallel directly? Why am I forming this ratio? Any idea? What did I say before about the individual sizes? Let's think about the static case again. What did we have to do to get a match between black holes and strings? So if I compute the size of a static string, do a random walk, and I can compute the size of a black hole, its horizon size. Yeah. I have to add self-gravitation. So here too, if I compute these sizes, I would expect them not to match because there's self-gravity. That's non-negligible. As I change the coupling, this effect is important. But it turns out that when you compute the ratio of these two things, it depends much more mildly on the coupling. So you would expect that self-gravitation works in all directions the same way. So if we take the ratio, we sort of cancel out this effect. All right? I know it's Friday, but it's still a morning session.
Sorry, this
Yes.
black hole string effect,
Yeah.
is it just a postulate, or do they actually calculate the
So you can compute the decay rates, and you can look at this regular Flam instability and see how fast it decays. And we discussed before decay rates for black holes. If you do that in this case, you find that it's faster than being within the Goldilocks range. So that's why this picture works. But then, of course, if you want to really do detailed computation with equal signs instead of wiggly signs, that's much harder, and much less is known about like these ultra-spinning objects. For example, not much is for some of these objects. As you go to very large spin, like these black bars, very little is known, analytically. There's a lot of like numerical solutions and so on. So it becomes really hard in higher dimensions at large spin to say something analytically. But this is the picture that we have based on, the general considerations. Okay, so let's try to verify this. Okay, let's go back to static strings, because we actually haven't computed the size of static strings yet. So the Hamiltonian for static strings is this level counting operator, which was these oscillators where we worked in light cone gauge. So these i's are just the transverse components. I is 1 to d minus 2, which I called C. So let me call it C here. So C is the transverse components. And then n equals 1 to infinity. We computed the partition function. Let me write it like that. So partition function was given by this infinite product of 1 minus e to the minus beta n to the power c. Beta was the inverse temperature. The thermodynamic limit, so taking beta to 0, we computed. Well, we computed at least the leading order effect, and then I told you what the logarithmic corrections is. Pi square over 6 beta with the transverse oscillators. Then we computed the density of states. So starting from the partition function, we can write this as, well, let me write it here. So z of beta was n equals 1 to infinity. The n, the density of states that we want to extract, e to the minus beta n. And we said we extract this how? Well, this sum is dominated by at large n, and we do a saddle point approximation to extract the density of states. And we found what it was. So it's given by e to the square root n, sprinkled with some factors of 2 pi and the number of the oscillators. And then there was a logarithmic correction that we also wrote down. And this was this generalization of the Hardy-Ramanujan result. And now, size of strings. Let me explain what I mean by size of strings. So, what is size of strings? So by this, I mean the mean squared radius of the string. So r bar squared, so the mean squared radius, which is defined as follows. So we had, a while ago, we wrote down the solution for the string. Then we went to light cone gauge, so we had only the xi's left. We evaluated xi at tau equals 0. And then we also have, so now I want to subtract the center of mass x. So this will just be the oscillators. And this I will take squared. So that's what I mean by the mean squared radius. There's also some normal ordering. And then there are some factors of the dimension and pi out front. And so this, if you work that out, if you plug in the oscillators, will give you the following expression. There's something that I defined to be called r square, capital R square, and r tilde square. and which, so these guys, so R square is, so when you compute that xi square, well, in that formula, there were the oscillators. And once you work out the product of these oscillators, you will find an expression in alpha minus n, alpha n. It comes with a 1 over n squared, because you multiply, there was a 1 over n guy, there was another 1 over n guy, you multiply them out. And then our tilde is the same, but with the alphas replaced by alpha tilde. And just a moment, and then there's also alpha, alpha tilde components that are mixed, but they will not enter in our computation. Yes? Oh, that's a pi. That's one of the most irrelevant things that are right on the board, at least since we are using wiggly mathematics. Okay, so now what we want to do is we want to compute this size, and we want to actually average over all states at the same level n. So we want to average over all states at level n. Okay? And this I will call these brackets r bar squared at level n. Okay? So if I look at the average value of this capital R squared, I will express it as an infinite sum of some coefficient, like we did for the density of states. So this is some coefficient. And then there's e to the minus beta n. And this average here, so putting the average on the left-hand side, well, gives me the average of this on the right-hand side. And this is then related to this Rn coefficient. So the thing that we have to compute at the end of the day is we have to extract from this average size value this coefficient. So this is the thing that we have to extract. But then also because we are averaging over states at the same level of n, we have to divide by the density of states, the n. So this is the thing that we want to compute. And it is obtained by looking at this expression for the oscillators, computing the average value, which essentially means we're computing, this is essentially computing the trace of e to the minus beta n with r squared, so like the expectation value. So this is that. And the n was just the trace of e to the minus beta n. So we have to compute the trace of e to the minus beta n r squared divided by the trace of e to the minus beta n. So this is the thing that we want to compute. So actually, I spare you the computation. I'm just going to motivate to you how to do that. So let me write this out again here. So this r squared, what I just wrote on the other side, is given by Rn squared, this coefficient, e to the minus beta n. And now it follows a similar strategy as extracting the density of states. So instead of computing, so we know this left-hand side. We could extract the density of states by computing an integral that we evaluate at large n using the saddle point approximation, and that was the result. Now a similar story here. We want to extract this coefficient from the trace of e to the minus beta n times r squared. And so there will be a formula for this coefficient Rn squared that involves an integral that we evaluate at large n in the saddle point approximation. Okay? So the thing that I have to compute is this trace of r squared. And this can be done in a similar way as we computed this partition function. Okay? So what happens, okay. So you can do this in a very similar way. So here I told you that, so this was trace e to the minus beta n. And we said that there is elementary methods from quantum mechanics that you can use in order to compute trace e to the minus beta n, where n is this expression, and out comes this right-hand side, 1 over 1 minus e to the minus beta n to some power. The same thing works for this guy. So n was given in terms of oscillators. R squared is given in terms of oscillators. A little different because there's a 1 over n squared. But you plug this in and you use your elementary methods from quantum mechanics in order to compute something similar to this expression. Once you have that, you equate it with this coefficient, Rn squared, e to the minus beta n. You write out a similar integral as we did for the density of states. You go to large n, so there's some e to the n times some function. You find the saddle point of that, and then you evaluate this expression, the saddle point approximation. What is the answer? The answer is as follows. Not sure why I kept the pi's, but okay, I did. So the answer is that Rn squared is proportional to the square root n times the density of states. So this was as a result by Mitchell and Turok from 87. So these are the two results that we need in order to compute the average size of a typical string state at fixed values of the level, the excitation level. Okay, so that was for the static case. And okay, so for the static case, now if I take these two expressions, nicely the coefficient R squared has already the density of states in it. So when we divide by it, I just have to take everything that's in front. And how does this scale? Well, this scales with square root n. So this size here scales as square root n. And does this remind you of something? So we discussed before the size of a string. I didn't explain to you how to do that computation, but we talked about random walkers. And we found that the random walk was square root of the entropy times the string size. So square root n is like the mass is like the entropy. Well, let me say like this. Square root is like the mass, and this is the way that random walkers behave. So we did an honest string computation for the size, and we find that it reproduces what the simple random walk picture told us. Okay? There was a question? Okay. So now let's generalize this to rotation. So there's a few changes that I have to do now. Okay, let me write them down again. So the change now is that the Hamiltonian will now involve also the angular momentum with a Lagrange multiplier. So this is the angular velocity, this is the angular momentum. And how do we give strings angular momentum? How do we do that? Well, actually, first of all, how do I define angular momentum of a string? How do I define momentum of a string? Yeah, but how do I define that? The symmetries, exactly. So you look at the symmetries of the string action. What symmetry do we have in flat space? We talked about that a lot. Let's forget about the super part. We have Poincaré symmetry, so we have translations and rotations. So translations give linear momentum, and Lorentz symmetry gives angular momentum. So the total angular momentum of the string, so you can construct the Noether currents for the string, and then the total momentum and the total angular momentum are constructed from that. So what do I have available from the string, from the solution of the string, that could give me angular momentum? So we had like the center of mass location, we had the linear momentum, and we had this bunch of oscillators. What can I use in order to make angular momentum? What inherently of the string can I use to make the string spin? The solution is given by center of mass, location, plus linear momentum, plus oscillators. What can I use? The oscillators. I have to put them in such a way that the string starts to spin. Okay? So if you write down your angular momentum, let's say we want to have it in a 1-2 plane, then you can spin it up by in the following way. So you can, we do 1-2 plane, spin in the 1-2 plane. So this will involve the oscillators 1 and 2. So you can figure out that this is what you have to do to have rotation in the 1-2 plane, just by looking at the symmetries and the conserved current that gives you angular momentum. So this will involve like the x mu of the spin of the string, the x mu, and then you know the solution of that, and you plug it in, and that will be what remains if you want to have angular momentum in the 1-2 plane. Okay? So then what happens to the partition function? So now the partition function will depend on not just beta, but it will also depend on this angular velocity omega. So I plug in this angular momentum in terms of the 1-2 oscillators. What happens is that this product of this 1/1 minus e to the minus beta to the n to the c, I will have to borrow from the c a piece such that I can incorporate the angular velocity, right? So I have 2 oscillators. So from this partition function with c powers, I have to borrow 2 of them such that I can have the effect of spin. You can check, take omega to 0, then these 2 become the same, and then the c minus 1 becomes c again. So this is the way to add spin to your partition function. You can do this via your elementary tools. Okay, so then let me keep this up for a little bit. So then we want to take the high temperature limit, beta to 0. So we do some similar analysis as for the static case. You have to work a little harder because now you have also these terms in the angular velocity. But the result is as follows. So the same thing as we had up there, this exponential and then the logarithmic correction. So let me color this. So these are the new things here. There's a new thing here, so there's a function in terms of the angular velocity that gets added to the partition function as an extra factor. And it goes like omega over sine pi omega. So this is the extra piece here in the high temperature partition function. And now if we want to extract the density of states like we did here, we have to take this into account. So writing z of beta omega as an infinite sum. There is now the density of states, which not only depends on n, but also j. So we have the density of states at fixed level and fixed excitation level and fixed angular momentum. So this was there before, this e to the minus beta n. But now I also have to go from this, so I go from the beta variable to the n variable, and I go from the omega variable to the j variable. So I also have to add an e to the beta omega j here. And then I want to extract the density of states, dnj. Okay? Okay. So I'm actually not going to write out this expression because it is really horrible. So this expression involves Well, it has some factors of n there, but actually n gets replaced by n minus j. The exponent here is more complicated. And then there's also the square of some hyperbolic sec, the inverse of there's some hyperbolic function in there as well. It's kind of ugly. In the large angular momentum limit, this was first computed by Russo and Saskind. And then we recently generalized this to other values of j. So smaller rotation, moderate rotation, small rotation. But from here you saw that if you're interested in sizes, you have to divide by the density of states. So that's why I'm not even bothering to write it down, because we have to divide it anyway. And if we're able to write the string sizes in terms of something multiplying the density of states, then I won't bother writing it on the board. Okay, and then the size of rotating strings. So again, we compute this thing Rn squared, so the average of the size of the transverse string component squared. And I'm just repeating what I wrote there for the static case. But now this coefficient will also depend on j. And we'll have these two exponentials there. And now I want to extract this guy. But because I have now two different sizes that I can look at the size in the plane of rotation and perpendicular to it. There are two sizes that I can compute. There is one that is sort of a parallel to the rotation plane. And then there's another one that's perpendicular to it. All right? And then I want to again compute this average squared value at fixed n and fixed j. And so there will be two of these that I can compute. Let me just write this in this form. So there will be two sizes that I will compute, one where I look at the parallel direction and one perpendicular to the rotation plane. So this is the last thing that I'm going to write down. I'm going to give you the result. And then we're going to compare this to the result of black holes and see if we can get a match between rotating black holes and strings. Okay, so the computation that you have to do is very similar to the ones that we had before. You have to sort of invert this sum you have to turn it into an integral over the partition function, now depending on beta and omega. So there's two integrals that you have to do. One is over omega and one is over beta. And that spits out something that depends only on n and j. So again, you do this in a saddle point approximation. The expressions are rather unwieldy because spin adds these more complicated functions. But at the end of the day, you get the following result. So for the string, in the perpendicular direction, this quantity over there, now written, I put back the string scale here so that I have numbers on the right-hand side. This goes as follows. So transverse to the rotation plane, I find the following sizes. So there are three regimes that we're looking at. One is order 1 in terms of n. One is where we look at angular momentum of order n. And remember, the entropy scales like square root n. So this would be much bigger than the entropy. This would be much smaller than the entropy. And here we're going to put a moderately spinning string that has of the order the size of the entropy. Okay? And mu here, mu is a number that is between 0 and 1. So one thing that you see is that in the direction perpendicular to the plane, the string indeed shrinks. So if you spin it up a lot, and j can be up to the order of n, the perpendicular size gets shrunk down. For moderate spin, you have a more moderate effect, but still it gets squeezed in the direction transverse to the rotation plane. And then for strings that rotate very slowly, the leading term doesn't even depend on j. So we'll have to do better to get the functional dependence in terms of J. Let me also give you the parallel size. So that goes as follows. And this is again for J of order 1, J of order square root n, and J of order n. So you notice that for the size in the rotation plane, the string spreads out quite a bit. So for highly spinning objects, the spread is enormous. The string wants to spread much more in the plane of rotation, then it gets squeezed in the other directions. Then for moderate spin, there's some number that is smaller than 1, so the string does get shrunk down. Sorry, this number is bigger than 1, so this is an effect that would make the string grow. But then there's an effect that makes the string shrink. And so there's some competition between these two effects. Okay? So now let's look at the ratio, which is the thing that we believe to be approximately adiabatically invariant. But before doing so, let me add corrections, subleading corrections to this small spinning regime. Because remember, the regime where the string and the black hole spins very little should be the regime where they match best. And here I don't see any effect of the spin because I just kept the leading order in the large n expansion. So let me put that back. So if I put that back, okay, this is a bad color. So if I put that back, I will get some number here, and then some other number divided by square root n for the perpendicular scaling. Here I'll get some number, some other number over square root n, and then the first place where the spin comes in, there's yet another number over square root n, and then j squared. You notice that these gammas here are the same. So the first few subleading orders are the same, but then at some point, at this order, there's a j dependence that comes in. And notice the square here. Okay, so now let me write down the ratios. Perpendicular over parallel. The string scale drops out. And I have the following. So take this ratio. What you find is that the first term is 1, and then the second term is of order j squared over s squared, where I have now written square root n in terms of s. So you divide the 2, there will be 2 powers. That is for j of order 1. Next is a constant, which is smaller than 1, because this constant c is bigger than 1. And then the third regime gives me s over j. Yes? These are just numbers. So when you do the computation, there will be some numbers in there. I'm not keeping track of overall factors. Remember, there are some overall order 1 numbers that we cannot hope to match between the correspondence, hence the proportionality. But the relative numbers here, they do matter. And what matters here is whether they're bigger or smaller than 0 or 1, depending on what you're looking at. So keeping this constant is relevant because, so there's an overall constant that is the same between the two. And then this one is extra. This is actually a slowly varying function. It's actually a function of j over square root n. But since j is of order square root n, this is also roughly speaking a number. And the form of this C parallel, you can read off that it is bigger than 1. So that's the only feature that you have to know about this number. And so this means that these two here are not equal, but they differ by this guy. And this is this smaller than 1 here. And what this tells you is that if you compute the ratio between perpendicular and parallel size, when you add spin, then it shrinks. And this is sort of the behavior that you expect. You expect the string to spread in this direction and to become smaller in that. And so you shouldn't find 1 on the right-hand side. So this is what this guy does. And then we see that the subleading correction in spin actually gave us this wonderful fact of j squared over s squared. This is also positive, so this is, the static case would be 1. The ratios of these two things would be 1. And then subtracted from there is something that has dependence on j squared over s squared. So now I need something to compare these two, so let me write down what we compare it to for the black hole, and then we end. So the thing to compare it to, so for the black hole, we have to come up with some notion of parallel and perpendicular. We chose one that seems to make sense and be simple enough. What's the result? If I compute the analog expression for the black hole, I get 1 minus, and then here I can write factors because these expressions are known exactly in all dimensions, and the dimensional dependence drops out. So there was a question before about dependence on D. It turns out that you can write down these radii exactly, and once you take the ratio, the information about the space-time dimension drops out. So these are the three regimes. By writing the entropy in terms of, so again, entropy is of order square root n. So these three regimes are the same as these. Now we can compare. Let's compare the first. So for strings, the dependence on the spin for a small spin is j squared over s squared. And look, it's the same for black holes. For moderate spin, there's some complicated number here, but it's smaller than 1. For black holes, it's also smaller than 1. Also some, this you can write down exactly. And then for large spin, we have a dependence on s over j, while for the black hole, we have a dependence on the square of that. Should this worry us? No, because we don't expect there to be a correspondence between highly spinning black holes and strings without the dynamics that we discussed before, without this Gregor-Laflamme and radiation death for highly spinning objects. So we see that the black objects and strings, they pancake. They pancake more for larger spins. But at large spin, we don't expect them to agree, so this doesn't worry us. But for small angular momentum, we do expect them to match. And we have seen that when we compute this object, which is an almost adiabatic invariant, then the two precisely match in the functional dependence, both on j squared and on s squared. There could have been a different functional dependence on s, but it has come out exactly the same way. Okay, so we have found one extra quantity that we can match across the correspondence point, thus giving more evidence that supports this picture. But there's many more things that you could try to make more precise and that you could try to match. But that's it. So that's where we're ending. So I discussed in this double lecture this idea that black holes can be described by strings, thus giving us a statistical interpretation of the mysterious area entropy formula at one value of the coupling. And we tried to make this picture more precise and more robust by checking that while we fix the entropy, various other properties of black holes and strings have to match at the correspondence point. And they do. Now you can go and figure out new properties other properties that you want to check, other things that you want to compute to make this picture even more robust. And maybe one day we will be powerful enough so that we can go from wiggly mathematics to exact mathematics. That would be a pipe dream, but yeah. I'll leave it at that. Thanks. If you have more questions, I'm still around until roughly 2:30, 2:20 or something. But then I'm gone, and I hope you enjoy the rest of your school.